Hi everyone, welcome back to Chem Help ASAP. In this problem set video, we are going to be working with gases. So we'll start with some questions about the properties of gases. We'll do some conversions between pressure units, and then we will start working with the gas laws. So we will work with Boyle's law, Charles's law, and the combined gas law. Then we will move into problems using the ideal gas law. Now we'll finish up with a couple of questions where we debate real versus ideal gases. Let's get started. Let's start with some properties of gases. My first question is, when you blow up a balloon, what shape does the gas take? Does this shape change as you add more air? And then what property of gases are you observing? Okay, so if you blow up a balloon, the shape the gas takes is simply the shape of the balloon. Now, as you add more air, the balloon does not necessarily change shape, it just becomes larger. Again, the gas is just taking the shape of the container. This is what sets gases off from solids and liquids. They have no definite shape and no definite volume. They will simply fill whatever container you put them in. My next question reads, a certain gas sample contains cations and anions. How would you expect the particles within the sample to behave? Well, remember, cations have a positive charge and anions have a negative charge. We would expect those two charges to attract. However, due to the kinetic molecular theory of gases, these particles ought to be so far apart that they do not experience any attraction at all. So they would behave as if they had no charge. Before we start working with gases, we need to be able to convert between units of pressure. So let's get comfortable with some unit conversions with pressure. Here is our first problem. Imagine Torricelli took his barometer up to the top of a mountain and measured 535 millimeters of mercury in his mercury tube. What is this pressure in torr, atmosphere, Pascal, and kilopascal? So we are simply going to take this 535 millimeters of mercury and convert to all these different units. Let's first convert to torr. The conversion factor between millimeters of mercury and torr is 1. So this is a very easy one. There is 1 torr and 1 millimeter of mercury. So this is 535 torr. Now let's take these millimeters of mercury and convert to atmospheres. There are 760 millimeters of mercury in an atmosphere. So here is our conversion. Our millimeters of mercury cancel and we get 0.704 atmosphere. Next, let's convert to Pascal. The conversion factor for Pascal is there are 101,325 Pascal in 760 millimeters of mercury. So here's our 535. Our millimeters of mercury cancel, and we get 7.13 times 10 to the 4th Pascal. For our final one, converting Pascal to kilopascal, we just need to divide by 1,000. So here is Pascal converted into kilopascal. That is 71.3 kilopascal. Let's do some more conversions. The pressure at the bottom of a 10-foot swimming pool is 1.35 atmosphere. What is this pressure in millimeters of mercury, torr, Pascal, and kilopascal? Our conversion factor from atmosphere to millimeters of mercury is in 1 atmosphere. There are 760 millimeters of mercury. You can see my atmosphere cancels and I get 1.03 times 10 to the 3rd millimeters of mercury. It's the same conversion factor for torr. Remember, 1 millimeter of mercury equals 1 torr. So again, if we start with our 1.35 atmosphere cancels and we get the same number for torr, 1.03 times 10 to the 3rd torr. To convert from atmospheres to pascals, again in 1 atmosphere there are 101,325 Pascal. Making sure our atmosphere cancel, we get 1.37 times 10 to the 5th Pascal. And to go to kilopascal, we just need to divide by 1,000. So here our Pascal cancels and we get 137 kilopascal. Now these conversion factors can always be looked up in a table. You'll find that you'll start to memorize a few of them as you do these problems, but they'll always be available to you. Let's do some problems with Boyle's law. A balloon is partially filled with a sample of gas. It has a pressure of 0.35 atmospheres. The initial volume of the balloon is 1.2 liters, and our final volume is what we're trying to calculate by increasing the pressure to 575 torr. I know this is Boyle's law because we are only given pressures and volumes, so we assume we're holding things like temperature and the amount of gas constant. Let's collect what we know. We know our initial pressure is 0.35 atmosphere. We know our initial volume, that is 0.12 liters. We know our final pressure, that is 575 torr. And we do not know our final volume, so that is what we're going to solve for. For Boyle's law, we need to make sure that our units match. So we need to either make sure both pressures are in atmosphere or both pressures are in torr. I'm going to convert this pressure 2 into atmosphere. Here we go. And now they both match. Here is Boyle's law. We have everything we need. Let's plug all of our numbers in. So here's our pressure 1.35, our volume 1.12. Here is our pressure 2 that we converted, 0.757, and we are solving for our volume 2. So now we just need to do some simple algebra, and our volume 2 is 0.0556 liters. You will get the same answer if you convert both pressures to torr as well. Let's do one more with Boyle's law. A sample of gas is placed in a sealed container of adjustable volume. Initially, the canister, let's see, it has a volume of 2.75 liters and a pressure of 2.6. So we are going to double the pressure, and we want to know what our final volume should be. Let's write down what we know. We know our initial pressure, that is 2.6 atmospheres. We know our initial volume, that is 2.75 liters. We know our final pressure, it is going to double. So our final pressure is 2.6 times 2, which is 5.2 atmospheres. And our volume 2, again, is what we are going to solve for. Here is Boyle's law. Let's plug in our numbers. We're plugging in our initial pressure and volume. Here is our doubled pressure, and again, we're solving for V2. Make sure your units are matching. And solve for this, we get 1.38 liters. Next, let's do a little work with Charles's law. This first problem says a balloon is filled with a sample of gas. So it occupies 35 liters at 15 degrees Celsius. We are going to lower the temperature to negative 30 degrees Celsius. Then we want to know what happens to the volume. Okay, let's write down what we know. We know our initial volume, that's 35 liters. We know our initial temperature, that's 15 degrees Celsius. We do not know our final volume, but we do know our final temperature at negative 30 degrees Celsius. Before we plug into Charles's law, we need to make sure that our temperatures are measured in Kelvin. So let's convert those now. Our 15 degrees Celsius is 288 Kelvin, and our negative 30 is 243 Kelvin. That is a very common mistake that students make when dealing with gas laws, is they'll forget to convert Celsius to Kelvin. You must always be in Kelvin. Okay, here is Charles's law. Let's plug in what we know. We know our initial volume and temperature. That's great. We do not know our second volume, but we do know our second temperature. Let's make sure our units match, and we have Kelvin. Now we can solve for V2. V2 is simply 29.5 liters. Here is our second Charles's law. Okay, so we have a sample of gas. It is initially 250 milliliters. We are going to heat the sample to 110 degrees Celsius, and our volume increases to 2.5 liters. What we are asked for is the initial temperature of the sample, and we want to get that in Celsius. Okay, let's write down what we know. We know our initial volume. That's milliliters. We do not know our initial temperature yet. We do know our final volume. That's 2.5 liters. And our final temperature is 110 degrees Celsius. We need to do a couple of quick conversions. We have our volume in milliliters and liters. So I'm going to convert this volume 2 into liters. Here we go. Again, all that matters is that your units match. Also, our temperature needs to be converted to Kelvin, so this 110 will become 383 Kelvin. Now let's plug into Charles's law. Here is our initial volume. We do not know our initial temperature, but we do know our final volume and our final temperature, so we can solve for T1. So our initial temperature is 68.9 Kelvin. Now our problem asked us for this temperature in Celsius, so let's just do a quick conversion. And our initial temperature is negative 204.1 degrees Celsius. Now that we've done Boyle's law and Charles's law, let's put them together and let's do some combined law problems. A movable piston initially has a volume of 150 milliliters and is filled with the gas initially at 475 torr. Okay, so the piston is expanded to 500 milliliters and our pressure drops to 300 torr and the temperature of the gas becomes 48 degrees Celsius. The question asking us, what is the initial temperature of the gas? These problems have a lot of numbers, so I always like to make a list of what I know. Our initial pressure, we know that is 475 torr. Our initial volume, we also know that is 150 milliliters. Okay, our initial temperature, we do not know that, so that is unknown. Our final pressure, yes, we know that's 300 torr. Our final volume, we also know that's 500 milliliters. And our final temperature, we do know that is 48 degrees Celsius. Because pressure, volume, and temperature are changing, we are going to be using our combined gas law. But before we plug numbers in, we need to convert this Celsius to Kelvin. So let's do that quickly. Okay, that is 321 Kelvin. Now we can actually put numbers in. Okay, so plugging in all our variables, we get this monstrosity. Let's double check and make sure our units match. We have torr and torr, milliliters and milliliters, and our temperature is in Kelvin. So now we just need to work our algebra to find T1. And T1 is 152 Kelvin. And let's convert that to Celsius. And we get negative 121 Celsius. Let's do another combined gas law. Okay, so we have a balloon initially at 0.95 liters. The pressure is 850 torr and the temperature is 20 degrees Celsius. Okay, so the balloon is released. It expands to 1.35 liters and the temperature drops to 7. And the question's asking us what the final pressure is going to be. Let's list out everything we know. So we know our initial pressure, that's 850 torr. We also know our initial volume, that is 0.95 liters, and our initial temperature is 20 degrees C. Let's go ahead and convert that to Kelvin. Here we go, 293. We do not know the final pressure, that's unknown. We do know our final volume, that is 1.35 liters, and we also know our final temperature is 7 Celsius. Converting that to Kelvin is 280 Kelvin. Okay, we can now plug this into combined gas law and get our final pressure. Here's our combined gas law. Here is all of our information in combined gas law. Let's make sure our units match, our liters are matching up, our Kelvin are matching up. So our final pressure is 571 torr. So far, we've used gas laws only in the sense of having an initial and a final condition. Let's now switch over to ideal gas law. Here's our first problem. We want to know the pressure of a sample of oxygen gas. We know the mass, we know the temperature, and we know the volume. We are also assuming that it is an ideal gas. Let's list out what we know. We do not know the pressure. We do know the volume. We do not know how many moles we have. We always know R. And we also know our temperature. Now we need to do some conversion. If you look at the units on R, you'll notice volume is in liters. So let's convert our volume to liters. Here we go. Also, our temperature, again, is in Kelvin. So let's convert our temperature to Kelvin. Here we go. The only thing we're missing so far is number of moles. However, we do have the mass of the sample and we know what it is, so we can convert that. Here's our 3.62 grams of oxygen using molar mass, making sure units cancel. We have 0.113 moles of oxygen. Now we can plug everything in to calculate that pressure. Here is our ideal gas law. Let's get all of our numbers in. So we're putting in our volume, our number of moles. Here's our value of R and our temperature. Whatever value we use for R is going to dictate all of our units. So we have liters here, liters in our volume. We have moles and Kelvin and Kelvin. So this means our pressure is going to come out in atmospheres. Now we can do our math and we get a pressure of 96.3 atmospheres. Let's do another one. What is the density of hydrogen gas at 85 degrees Celsius, 95,100 Pascal, and it occupies 2.25 milliliters? Let's list out what we know. We know our pressure, we know our volume. Let's get a value for R. Here is a different value for R, and our temperature we do know is 85 degrees Celsius. Looking at this value of R, we're going to need to do a couple of conversions. So our pressure needs to go to torr. So let's convert Pascal to torr. Okay, that is 713.3 torr. Our volume also has to go to liters. That's an easy conversion, so convert that. We have 0.0278 liters. And of course, our temperature has to go to Kelvin. We have 358 Kelvin. Now, if we're calculating density, we are also going to need the molar mass of our gas. Because our gas is hydrogen gas, our molar mass is 2.0159 grams per mole. All right, here is our equation for calculating the density of a gas. Now let's plug in all of our numbers. But before we do our math, let's make sure of our units. Okay, our torr is going to cancel. That's great. Our moles cancel, our Kelvin cancels, and we are going to be left with grams per liter. That's perfect. That's exactly what we want for density. Now doing the math, we get 0.0644 grams per liter. Now, usually we measure density in grams per milliliter, so I'm going to go ahead and convert that liters into milliliters. And I'm going to get 6.44 times 10 to the negative fifth grams per milliliter. You can see that gases are not very dense, which makes sense. Let's do another problem with a twist on ideal gas law. Calculate the molar mass of a 0.981 gram sample of an ideal gas, and we're at 560 torr, 20 degrees C, and we have a volume of 1.69 liters. Okay, listing out what we know. We know our pressure. Okay, great. We know our volume. We do not know our number of moles, so that is unknown. We always have R. Here is our value for R, and we've got temperature. Looking at the units of R, we already have pressure in torr and volume in liters. We just need to convert to Kelvin, so let's convert our temperature to Kelvin. There we go. And we also know that the mass of our sample is 0.981. Here's ideal gas law. Let's plug in what we know. So we plug in our pressure, our volume, our R, and our temperature. Again, let's make sure that our units are working. Torrs cancel, liters cancel, Kelvin cancels. This will give us moles. Perfect. So we will have 0.0518 mole. But our problem asked us to calculate the molar mass. Well, remember, molar mass is simply grams of sample over moles of sample. We just calculated our moles of sample, and our problem gives us the mass of our sample. So we should be able to plug these in and get our molar mass. Here we go. Here are our numbers plugged in. Our molar mass is 18.9 grams per mole. Our units really did lead us with this problem, didn't it? We cannot finish gases without doing some stoichiometry. Ammonium nitrate decomposes when heated. The reaction is shown below. Okay, great. Oh, and it looks like they balanced it for us too. Fantastic. If 45 grams of ammonium nitrate fully decompose at STP, how many liters of nitrogen gas and water vapor are formed? Remember, when we're doing stoichiometry, we always want moles. So let's first convert to moles. So we have 45 grams of ammonium nitrate. We need to first convert that into moles. So using the molar mass, our grams of ammonium nitrate cancel. That gives us moles of ammonium nitrate. Now to go to moles of nitrogen, we need our mole ratio. And the nice thing is this is a 1-to-1 mole ratio. So our moles of ammonium nitrate cancel, and we get 0.562 moles of nitrogen. Let's do the same thing for our water vapor. Again, starting with our 45 grams of ammonium nitrate, convert that to moles. Now we have a different mole ratio because we are predicting water here. This is a 1-to-2. Our moles of ammonium nitrate cancel, and we will get 1.12 moles of water vapor. So we've done our stoichiometry, but our problem is asking us for volume. It wants liters. Now, the nice thing is we are at STP. When we are at standard temperature and pressure, we know that every mole occupies 22.4 liters. So this becomes a simple conversion. Starting with our moles of nitrogen, here is our conversion factor. Our moles cancel, and we get 12.6 liters of nitrogen. We do the same thing with our water vapor. Here is our 1.12 moles of water. Again, make sure moles cancel, and we get 25.1 liters of water vapor. Now, I do want to caution you, this conversion factor here only works at standard temperature and pressure. Once you are not at STP, then you need to go back to ideal gas law. Let's now work a problem when we are not at STP. So aluminum reacts with hydrochloric acid to form hydrogen gas as shown below. And again, the nice thing is the equation is already balanced. How many grams of aluminum are needed to form 850 torr of hydrogen gas at 85 degrees C, and our reaction chamber is 90 liters. We have a lot of numbers here. Let's make a list. We know our pressure, it's 850 torr. We know our volume is 90 liters. We do not know how many moles we have. We always know our value for R, and our temperature is 85 degrees Celsius, which is 358 Kelvin. Looking at our list, we can calculate our moles of hydrogen gas. So let's plug what we know into ideal gas law. Okay, here is our pressure and volume. We have our R and our temperature. Let's cancel out our units. Okay, torr and liters and Kelvin. So we will get moles out. So we have 343 moles of hydrogen. Now our problem wants to know how many grams of aluminum. So far we have only used ideal gas law. We need to now do stoichiometry to convert from the hydrogen to the aluminum. Here are our moles of hydrogen. Our mole ratio is right here. Remember, make sure your hydrogens cancel. Now we have moles of aluminum, but our problem asks us for grams. So one more conversion factor. The molar mass of aluminum. That will give us grams of aluminum. And so our final answer is 61.6 grams of aluminum. I know that gas stoichiometry problems can feel very overwhelming with the amount of information given in the problem, and it feels like the answer is so far away. What I find helps me is to make a list of what I know. And once I've made that list, then usually it helps me determine what my next step is. So far, we have assumed that all our gases are behaving like ideal gases. But of course, we do not live in the ideal world. We live in the real world. So let's talk a little bit about real gases. So here is our question. Which gas would you expect to behave more like an ideal gas, and why? Helium at 25 degrees C or hydrogen at 250 degrees C. So we have a gas at a low temperature and a gas at a high temperature. We get better ideal behavior at a high temperature, so our hydrogen at 250 degrees C will behave more like an ideal gas. Here's our next problem. The decomposition reaction of sodium hydrogen carbonate is shown below. When would you expect the products of this reaction to act like ideal gases? At the start of the reaction or at the end of the reaction, and why? We know that ideal behavior happens at low pressure, not high pressure. So when is this reaction going to have its lowest pressure? Well, that's going to happen at the very beginning of the reaction because we have not formed much of our carbon dioxide or our water vapor, so our pressures would be very low. So this reaction will mimic ideal behavior at the very start of the reaction. I hope that working these problems together has helped you understand gas laws better, and thanks so much for watching.